Welcome everyone to our afternoon session of the annual meeting of the UK Center for Topological Data Analysis. And our first speaker is Professor Ginestra Bianconi, who will talk about topological Dirac operator and the dynamics of topological signals. Over to you, Ginestra, please.
Thank you so much, Vitali, for the nice invitation and introduction. It's a real pleasure to be here. And today I want to tell you about some work on topological operator. And we will discuss about the higher order Laplacian, some novel result about higher order Laplacian, and also about the topological Dirac operator. And then if time allows, we will cover the dynamics of topological signals, and in particular, synchronization models. So I'm coming from the field of complex networks and complexity. And from this perspective, simplicial complexes are raising increasing attention. And the reason is that the majority of complex systems are actually not only encoding pairwise interaction captured by network, but also higher order interaction between two or more nodes. And therefore, they require the use of simplicial complexes that are formed by node, links, triangle, tetrahedron, and so on. An example of these simplicial complex data sets are found in brain data, where you see, for instance, 3 regions of the brain, and you want to distinguish between different situations in which the 3 regions of the brains are correlated pairwise, or if they are activated at the same time with a 3-body correlation function. Or in biology also, we have protein interaction, which usually include more than 2 types of protein organized in what are called protein complexes. So really, to understand how protein interact to perform a given function, we need higher order networks, so simplicial complex, but also cell complexes. And in social networks also, simplicial data are ubiquitous, and we have, for example, of face-to-face interaction, which can include more than 2 individuals, and of course, collaboration network, which include both, actor collaboration network or also scientific collaboration network, when you can have a paper co-authored by more than 2 authors. So in this context, of course, higher order networks are so becoming more and more fashionable and used. And in general, in this context, there has been a lot of discussion about the interplay between the structure of networks and their dynamics. And in the context of network, and also in the context of higher order networks, there has been a lot of focus and discussion about the role that combinatorial and statistical property has in determining this interplay between structure and dynamics. But actually, it is emerging that a much richer scenario in which this interplay is actually mediated by simplicial geometry and simplicial topology as well. And so here in this talk, we will cover we will show how some geometrical aspect of higher order network can affect higher order dynamics, and also we discuss in length how topology can affect higher order dynamics. So our main focus will be on topological signals. So while in network there has been a lot of attention to dynamics on network, which is understood to be a dynamics of variable associated to the node of the network, when you embrace a topological perspective, you might want to associate a dynamical variable also to links or to triangles or to higher order simplices of your simplicial complex, which go under the name of topological signals. And actually these topological signals of different dimension can even interact one with another one. So example of topological signals are starting to be considered, although data is not as ubiquitous as signals defined on the nodes. An example of topological signals are citation in a collaboration network. So you can imagine three authors and three co-authors, and the citation that papers co-authors by these three people have got, or a synaptic signal. So in neuronal network, you can have neurons interacting via neurotransmitters, and this synaptic signal can be also modulated by other cell like glia. And so the dynamical signal is another variable associated to the edge. And in general, edge signal in the brain are gaining increasing attention, and there is very interesting work by Olaf Sporn, for example. All these signals are co-chain, but actually there are also topological signals that are vector field, like the speed of wind at given location or the current at given location in the ocean. But also, if this last example are vector field, the fact is that you can treat vector field as co-chain, because practically you project the vector field on the edges of the underlying triangulation, for instance here of the surface of the Earth, and you can treat them as topological signals. So typically topological signals have been treated by considering the action of Hodge Laplacian, and here I introduce mostly for the notation that we will use here. I understand this audience is very familiar with Hodge Laplacian, but just to tell you a bit the notation we will use here. Of course, if we want to define the Hodge Laplacian, it's important to define the boundary operator, which map n chain to n-1 chain. So given a given set of n-dimensional simplices, the boundary operator, which is a linear operator, is defined by its action on each simplex. And so the action of the boundary operator of each n-dimensional simplex is a linear combination of the n-1 simplices at its boundary with an appropriate sign. So for instance, the boundary operator on the link 1, 2 is 2 minus 1. The boundary operator on the triangle is the link 1, 2, 2, 3 minus 1, 3, because you go around the triangle and you describe the boundary of the triangle. Of course, the boundary of the boundary is null. So if you concatenate two boundary operator, you get the null operator. And this is easy to check in this example of the triangle. And for what concerns this talk, is very important to tell you that we will use this a matrix representation of this boundary operator, and we will call this matrix incidence matrices, which are rectangular matrices. So B1 is a rectangular matrix between node and links, having column for each link, the boundary of that link. So for 1, 2, the link 1, 2, we have 1, 2, the node 2 minus the node 1, and the incidence matrix B2 is a representation of the boundary operator of second order. So we have that the boundary of the triangle is 1, 2 plus 2, 3 minus 1, 3. So interesting, the graph Laplacian, which is very popular for people working in graph networks from graph theory, but also complex network. And the graph Laplacian describes diffusion dynamics on a network, can be expressed as the product of the incidence matrix in this way. And interesting, the higher order Laplacian can also be defined similarly, and they describe diffusion from n simplices to n simplices. And this diffusion can occur upping to n-1 simplices. This is the first part of this right-hand side, or there can be up to n+1 simplices. So this first part is called ln down, and the second part is called ln up. So ln down describes diffusion from n simplices to n simplices through n-1 simplices, and ln up describes diffusion from n simplices to n simplices to n+1 simplices. And the very celebrated property of this higher order Laplacian is that the dimension of the kernel is the n-Betti number, and of course they obey Hodge decomposition, so that any n-chain can be decomposed in its harmonic, irrotational, or solidonal component. So here I introduce to you some more physical physics kind of description of this operator, and this is inspired by the problem of finding good definition of dimension of a network. And so physicists like to call the Hausdorff dimension or fractal dimension a quantity that describes how the diameter of a network changes with the number of nodes in the network. Of course, this Hausdorff dimension is defined as the number of nodes goes to infinity, so you should have a model for which you can go at larger and larger size. And for a d-dimensional lattice, the Hausdorff dimension is equal to the dimension of the lattice. For what are called small world network, where this diameter scale like the logarithm of n, the Hausdorff dimension is typically put to be infinity. But there are also other types of dimension, like the spectral dimension, which describe the property of diffusion on a network. So what is the dimension perceived by diffusion process acting, moving on a given network? And for that, we need the graph Laplacian, which of course is semi-positive matrix. In a connected network, we have only one zero eigenvalue. And then this second smallest eigenvalue, or Fiedler eigenvalue, is typically very much celebrated because it sets this typical scale for relaxation of diffusion processes to the steady state. And typically this relaxation is exponential when this mu2 is finite, and mu2, the inverse of mu2, set the scale for the typical time to relaxation. But actually, in many geometrical network models, such as lattices, or as we will see, hyperbolic geometry, where you can go in the infinite network limit, so you have a way to explore this limit, the Fiedler eigenvalue goes to zero as the network size increase. And in this case, we say that the spectral gap closed. This means that the characteristic time diverge for relaxation diverge, and you don't have any more an exponential relaxation. And in particular, what can happen in many networks is that there is not only lambda2 that goes to zero, but there is a hierarchy of small eigenvalue that is described by this density of eigenvalue scaling as a power law. And this power law, the exponent of this power law, is determined by this spectral dimension ds. So that you have a hierarchy of eigenvalue that gives you this slow relaxation, typically power law relaxation dynamics of diffusion process. So on a square lattice, for instance, this is very much understood. So the spectral dimension is the dimension of the lattice because practically the eigenvector are the Fourier mode, and so the eigenvalue are connected with the wave number of this Fourier mode. And you can do this, that is typically called density of state in physics. But you can generalize that to other network, And for instance, what we can see is that you can consider also hyperbolic network, and a class of interesting hyperbolic network are Apollonian or pseudo-fractal networks or simplicial complex, in which we start at time t equal to 1 by single d simplex, and at each time we glue a d simplex either to a d-1 phase only added at the previous iteration, or to any d-1 simplex added at any of the previous iteration. In one case, we have a manifold. In one case, we have a hyperbolic in the sense of Gromov network, but it's not anymore a manifold. So we have kind of explored this model using also a much wider model, including stochasticity. And so we can start from a single d-dimensional simplex, and each time glue a d-dimensional simplex with a new node to a d-1 phase. And we have a particular probability on with whom we link this phase to the this simplex to the d-1 phases. And we can generate manifold, and this hyperbolic manifold like this for d equal to 2, which are generating this random Fere graph. So we have, again, we are interested in this also because it's a fully stochastic model which automatically generates some network geometry. And we can extend this also to three-dimensional simplicial complex. So we start with a tetrahedra and we stack tetrahedra one across the other, along the face of the other tetrahedra. So interesting, all these models have a Hausdorff dimension which is infinity, or they are small world, and they have a spectral dimension which is finite and greater than 2. So what we find that is more surprising is that it's not only the graph Laplacian that has this spectral dimension, but any of the m-order up Laplacian have a different spectral dimension. So actually the diffusion occurring from node to node through link, or from link to triangle and so on, has different spectral dimensions, so different statistical property. And we have predicted this spectral dimension with a renormalization group approach, looking for a Gaussian model in which we calculate the free energy, and then by differentiation we get the density of state. We have done this with a slightly different definition of the up Laplacian, so the normalized up Laplacian. And we consider this RG flow. So I don't want to go on the detail of this, but we are able to find this scaling of the power law for any dimension, for the Apollonian and for the pseudo-fractal network. Of course, these are very regular structures, so that you see some degeneracy of the eigenvalue, which is due to the symmetries, but the scaling of the power law is fully captured. And these are the NGF, so the network geometry with flavor, have a different spectral dimension, always finite, and less degeneracy of eigenvalue. And interesting, we can do this theory and we can predict this spectral dimension for any dimension of the simplicial complex and any dimension of the higher order up Laplacian that we look. So for instance, take a 4-dimensional simplicial complex, we can predict the spectral dimension of the second order, the third order, and the fourth order up Laplacian. Sorry, the 2, 1, and 0 order up Laplacian. So For NGF is more difficult to predict the spectral dimension, but we can look at this numerically. We can find different value, and we can study diffusion, right, with this higher order Laplacian. So diffusion from n simplices to n simplices to n-1 or n+1 simplex. We can also, in some sense, since not always we have a stationary state, because not always this higher order Laplacian have a zero eigenvalue if the Betti number is positive, is zero, sorry. And so we can remove the contribution from the smallest eigenvalue in order to have always a non-trivial steady state. So what we found is that the return time distribution differs depending on the order in which we define the diffusion. So, you know, for instance, we have a three-dimensional simplicial complex, and we consider diffusion from node to links, so from links to triangle, or triangle to tetrahedra, and we find different statistical property of this diffusion process. So the same simplicial complex can sustain diffusion process that have different property, because the spectral dimension in general can be different. So let me now move to the second operator I want to discuss in this talk, and this is the topological Dirac operator, on which I've been working quite recently. So while the n-order Laplacian operator only acts on n-dimensional signals, the Dirac operator can couple signals of different dimension. So it acts on a spinor which has two components, two blocks. The first block is a 0 cochain, and the second block is a 1 cochain. And so the Dirac operator is as this block structure in which in the off-diagonal term you have the incidence matrix B1 and B1 transpose. So you go from link to node and from node to links, and you can introduce a rotation in the complex plane with this complex number which absolute value 1. And the main property of this topological Dirac operator, why we call it Dirac operator, is that is the square root of the Laplacian. So if you do the square, you get the Laplacian matrix. So Laplacian L0 Laplacian and L1 down Laplacian for a network. So we can define the topological Dirac equation. So define an Hamiltonian in which we have the Dirac operator, mass, and this beta matrix, which is in the diagonal as 1 and -1. And we notice that D and beta anticommute. And actually, we can study the eigenstate of this Dirac operator. And we find that the spinor, which is the eigenvector, has two blocks, the 0 cochain and the 1 cochain, which are respectively left and right eigenvector of the incidence matrix. And the energy obeys the relativistic expression. So you have a positive branch and a negative branch of the energy. So this is just can be just obtained by looking at element by element, rearranging, and then apply E plus M to the first equation, E minus M to the second equation, and you find again that phi is the eigenvector of the graph Laplacian, and chi is the eigenvector of the L1 down Laplacian. Interesting. So interesting, you can do this on any network, right? You can study the energy eigenstate of the topological Dirac operator or any network. So you are coupling node and links, and these are example of some fungal network that are found in the literature. And here I apply this Dirac operator where the color is the value of the eigenfunction there. So regarding the density of state, so we have this symmetry between matter and antimatter for any energy which in absolute value is greater than the mass. So we can calculate this density of energy state. But interesting, this symmetry breaks down for energy which in absolute value are equal to the mass, because these are corresponding to the Betti number beta 0 and the Betti number beta 1. So in general, for a network, if you have a chain, these are equal to 1. Beta 0 and beta 1 are equal to 1 and equal to each other. But in general, for a network, this is not true. So you have this breakdown of matter and antimatter. And actually, for physicists, here in this case, the sign of the mass is not dictated a priori, so it can be also negative. So the role of mass and antimass can be exchanged. So we can apply this also to simplicial complexes, and we will have a larger spinor, including, for instance, for three-dimensional simplex, a 0 cochain, a 1 cochain, a 2 cochain, a 3 cochain, and we can generalize the Dirac operator. Here we see an example of this generalization. And interesting, the eigenstate couple always n-dimensional and n+1 dimensional topological signals, because since the boundary of the boundary is null, they are coupled one with the consecutive one. And so the energy, the density of energy state has different bands. And for this NGF, which have a different spectral dimension, you have, these energy bands that have different slope. And of course, you can imagine that probably you can put an interaction to induce some transition from this state, but for the moment, this state do not interact, do not speak to each other. Finally, we can consider the fact that if you have lattice, for instance, there is a different type of link, the X link, the Y link, the Z link, and you can play with this complex number, with this rotation that you induce when you go from node to link, and you can apply different rotation depending on the different type of links. And in 3 dimensions, you will need to use Pauli matrices, so you will need to increase the size of your spinor in such a way that now it has a block structure of 2 0 cochain and 2 1 cochain. So the incidence matrix, now you can decompose in incidence matrix working only between nodes and a given type of link, X link, Y link, Z link. And the Laplacian will be the sum of the Laplacian acting on X, Y, and Z direction. And interesting, for a lattice, you have the property that this Laplacian commute, right? So you can diagonalize them together simultaneously. So the Dirac operator is Hermitian. It has this off-diagonal block structure, and these matrices here are described by these Pauli matrices. So you can induce some rotation. These Pauli matrices as just the equivalent of this complex number, but they induce some rotation that is different from different type of links. So the Dirac equation reads in this way now, and you have always a relativistic dispersion relation, although there is this important property that the Dirac operator do not anti-commute. And actually, it's not only that they do not anti-commute, but also they do not commute when you consider node and links. This is a very interesting property. And we have applied this to some kind of blindly, for a kind of joke, we have applied this to multiplex networks. So multiplex networks are networks in which you have interaction of different type. For instance, a set of people which speak via email or mobile phone. And so if you have two types, you have that any two nodes can interact via two links, two type of links, or just one in one layer, or just one interaction in the other layer. So you have three type of this called multi-link. And so the dispersion relation remains relativistic. The Laplacian is the sum of the Laplacian associated to each multi-link, but now you need to be careful because this Laplacian associated to different multi-link will not commute, so will not be, it's not possible to diagonalize all these Laplacian simultaneously. So yeah, I want to just, so this is the main part of the talk, so describing this operator. And now I want just to try to give you a flavor of what we have done for synchronization of these topological signals. So how we have used the Hodge Laplacian and how we have used the Dirac operator for synchronization of topological signals. So synchronization is a fundamental dynamical processes, observing neurons, fireflies, but also just-at-random junction, also power grid. And you have practically, traditionally, you assume to have a dynamical variable, a phase associated to a node. Each phase rotates at its own frequency, but then phases associated to nearby node are coupled to the link of a network, and they try to align their phase. And this tendency to align the phase is modulated by a coupling constant sigma. And what you have is that as a function of sigma, you have an order parameter which tell you if there is this collective phenomenon that the phase start to synchronize, to have a collective motion that is like a given frequency, collective frequency, or not. And this is fully understood on a fully connected networks. On sparse networks is still very challenging. So there are several reliable approximation, but it's not a complete mathematical solved problem. So what we have done is to extend this framework to higher order Kuramoto model on simplicial complex, and this is joint work with Ana Paula Mignan and Joaquin Torres. So first of all, we noticed that the Kuramoto model can be expressed in terms of the incidence matrix. So theta is the phase associated to node, omega is the frequency of the node, sigma is the coupling constant, and here the sign is taken element-wise. So in order to define a topological synchronization of phase associated to links, for instance, or to triangles, we consider the natural extension using higher order incidence matrices. And now, of course, an important question is how can we, given a dynamics on n simplices, what is the dynamics induced on n-1 phase or n+1 phases? So for instance, if you have dynamics on links, what is the dynamics induced on node and triangles? And of course, you use the boundary matrix, the incidence matrix, and you apply, for instance, the discrete curl or the discrete divergence. And then these projected dynamics totally decoupled, and they are dictated by the Laplacian down, n+1 Laplacian down, and n-1 Laplacian up. And they describe a dynamics that is synchronized at zero coupling. And it describes, in some sense, the synchronization of the irrotational and solenoidal part of the signals independently. So, but actually, if you look at the original n-dimensional signal and a naive order parameter, you see nothing. You see nothing because these two parts, the rotational and the solenoidal component, might synchronize at different frequencies. So what you need to do is to filter up, filter the signal with the Ln down or Ln up, and then you are able to see the synchronization of this dynamic. So only if we perform the correct topological filtering, we can reveal this higher order synchronization. Okay, so how to couple the dynamics of node and links. So this is a work with Lucille Carmon, which is here, Joaquin Restrepo, Joaquin Torres. And what we want to do is to couple now the dynamics, not only what I discussed before was the dynamics defined on n-dimensional simplices and then projected on node and triangles, for instance. But now we want to consider the dynamics defined on nodes and the defined on links and how they interact together. And of course, we will make use of the Dirac operator. So the uncoupled dynamics on a network, this is the Kuramoto dynamics. This is the higher order Kuramoto dynamics defined on the links. We don't have B2 because there is a network, there are no triangle. So this can be expressed as a single equation with the Dirac operator. So where phi is signals defined on node and links, omega is the frequency of node and links, and D is the Dirac operator. So this is still uncoupled dynamic because as we will see, this when we operate D over sine of D, this is like something that decouple the two dynamic. Now theta depends only on theta and phi depends only on phi. But we can consider phase lag, so phase lag of the dynamics on the nodes that depends on the dynamics of the links, and a phase lag on the dynamics of the links that depends on the dynamics of the nearby nodes. And we do that by considering here inside the sine function higher order power of the Dirac operator, so practically the Laplacian. And we normalize this Laplacian with the matrix of the degree of the node and the degree of the links. And we have a matrix gamma, which is the same definition of the matrix that I previously called beta. And so the dynamics on the nodes is now, as you see, affected by a phase lag depending on the dynamics of the links, and the phase of the dynamics on the links is now depending on a phase lag depending on the dynamics of the node. So we project the dynamics of the links on the node, and we find a very noticeable result that the order parameter now are coupled. We don't have only the order parameter depending on the node signal or on the link signal, but we have order parameter depending both on t times psi, where psi is these links as projected on the node, and psi minus theta. So we have a full theoretical understanding of this model, which has a coherent phase and incoherent phase. And this is fully captured by considering the solution as stationarity. And we find that in this assumption that the signal is stationary, we find the same equation of the standard Kuramoto model. So we could consider that, this is when the Kuramoto model is defined on a fully connected network, we can consider that we would have in our case the same phase diagram of the standard Kuramoto model, so with the transition predicted to be at 1.56. And instead, we push our theoretical understanding by capturing the stability of this solution. And we find that this topological synchronization is a much richer phase diagram. So it has a discontinuity. So as you reach this coupling constant, you increase this coupling constant, the phase abruptly synchronize all together. And when you reduce, they go more slowly. They go in a continuous fashion, they go to zero. But actually, also the coherent phase becomes unstable, and it becomes the system reach what is called a rhythmic phase. So we are able to predict this jump. So this phase transition, so this would be node and link phase order parameter. Now on the right, we have couple order parameter of combination of node and link signals, which are discontinuous. And these are the theoretical prediction in the stationary state. And we have discontinuity both on R alpha and R beta. And actually, in this predicted unstable solution, we see that the order parameter start to oscillate with a rhythm that is not induced by the average of the frequency that we impose. So we are moving in the same frame of the average velocity or average frequency of the intrinsic frequency, and yet we see this oscillation. So these oscillations are induced intrinsically by this topological coupling. So this is a beautiful figure that Lucille has produced, showing what happens to this order parameter as the coupling constant decrease, and you see it oscillate almost periodically, but sigma is decreased now, so it's spiral out until it reaches the incoherent phase. So I conclude now. Topological synchronization for coupling topological signals of node and links is explosive. So it's much richer than topology dynamics only of node and only on links, and give rise to this rhythmic phase that can be related, for instance, to brain rhythm. So it would be a topological, fully topological scenario in which one can get this rhythmic phase. So in conclusion, topological signals allow us to combine topology and dynamics. Hodge Laplacian acts on signal of a given dimension, while the Dirac operator allows to couple signal of different dimension, and topological dynamics is very rich. So for instance, this topological synchronization, which use the Dirac operator as this continuity and this rhythmic phase. So I finish with this take-home message. So the interplay between higher order networks and higher order dynamics is dictated both by network geometry and topology, in addition to the statistical and combinatorial property of higher order network. And these are the reference of which I spoke. Thank you so much for your attention.
Thank you, Ginestra. Let us thank Ginestra, please. Right, very good. So as usual, before we start with questions, let me remind you that the next talk will be in about 7 minutes. So this is a break. So if you need some comfort break, please go take tea or coffee if you wish. And if there are any questions now, yes, for Ginestra, please. Let me stop.